Hey everyone, welcome to the team. If you're listening to this, you're officially part of the core engineering crew building silkDE, the desktop environment for Sexos. As a fellow engineer who's been down in the trenches with you, I put together this internal onboarding explainer to map out exactly what we're dealing with. Look, we're operating inside a really strict, no-nonsense, bare metal microkernel environment. We are not in Linux anymore. If we treat this system like a standard POSIX environment, we are going to immediately break our builds and completely tank our stability. So consider this explainer your absolute cognitive map to the system contract we all share.
Here's the quick rundown of what we're going to cover to get everyone calibrated. First, the Sexos reality. Second, silkDE component roles. Third, strict PDX data flow. Fourth, the invariants you absolutely cannot break. And finally, our current development priorities. Let's get right into it.
All right, Section 1, the SexOS reality. Right at the top of our foundational internal doc, agent_readme_first.md, it explicitly states, this is not Linux user space. No POSIX assumptions. We are building on an extremely strict, no-stand Rust microkernel. What does that mean for us practically? It means absolutely zero standard library, no libc, no hidden heap allocations hiding inside your loops, no standard threads, and definitely no sleep or time APIs unless we provide them locally. Every single binary we compile has to be a position-independent executable, or PIE. Seriously, if you bring standard Cargo web app thinking into this repository, the build will fail, or worse, you're going to trigger a hard hardware panic. So the architectural model we use to pull this off is called a SAS, a single address space operating system. Now, in a traditional OS, processes are isolated by switching page tables, right? But that costs thousands of CPU cycles. We don't do that. Instead, we collapse the entire OS into one global 64-bit virtual map. So you might be wondering, how on earth do we isolate memory? Well, we use hardware-accelerated Intel memory protection keys. You'll hear this called MPK or PKRU. A domain switch here costs us roughly a mere 20 to 40 cycles. It's incredibly fast. The CPU hardware itself strictly forbids any thread from accessing memory unless it physically holds the correct 4-bit key right there in its PKRU register. Because we don't have those standard tools, you've got to rewire your brain and use their physical equivalents from our translation matrix. Need a standard sync mutex? Nope. Use an atomic U64 with acquire and release ordering. Catch yourself reaching for a dynamic heap allocation like vec_new? Stop right there. You need to use a static array with a length counter. What about a standard thread sleep? Absolutely not, no way. Instead, you spin on a safe_Pandorix call, or you check the VBLANK counter. Our runtime has to be completely deterministic, so we rely entirely on monotonic tick counters, not wall clock APIs.
Moving on to Section 2, silkDE roles.
This right here is the strict capability graph locked in by our architecture.md. We have 3 main components, and everyone needs to know exactly what they do. First up is Silkshell. This runs under Protection Domain Key, or PK3. It completely owns all desktop, window, and input policy. Second is silkbar. Think of this strictly as the shell Chrome and top strip state producer. It only produces render intents. It does not actually draw anything. And finally, we have sexdisplay. This operates securely under PK1, and it is our sole compositor and hardware interface manager. I want to really emphasize this next point because it's absolute architectural law. Sexdisplay is the unquestionable sole owner of the physical frame buffer. It is literally the only component in the entire operating system that's granted the hardware capability to write pixels. Silkshell and silkbar, they never touch the frame buffer directly. If you try to get clever, bypass this, and write a direct cross-domain pointer to the screen from the shell, that Intel MPK hardware lock is going to immediately slap you with a segmentation fault. We used to have split-brain authority over the display, but that was a legacy bug, and we totally eradicated it. Today, sexdisplay interprets the frame graph and performs the final atomic commit. End of story.
Okay, Section 3 is strict PDX data flow.
Let's trace the exact causal chain of data across those hardware keys. You can think of it kind of like an interconnected staircase. Step 1. Sex input captures a raw HID event, like a key press or mouse move. Step 2. It routes this as an OP_HID_event straight to Silkshell. Now Silkshell gets it, applies whatever interaction policy makes sense, and decides, hey, the desktop needs to update. Step 3, Silkshell formulates an IPC payload that fulfills the silkbar update contract, specifically an OP_silkbar_update, which basically encodes the new UI state directly into its own memory.
Finally, step 4, sexdisplay receives this instruction, reads that shared memory, and commits the actual pixels to the screen. And the way we actually transfer that data, it is ridiculously fast. We use zero-copy IPC, which is a core architectural feature of Phase 30. Remember, we are not building some legacy message-passing OS. We are a capability-controlled shared memory substrate. When Silk Shell needs to send an update to sexdisplay, it absolutely does not copy the frame buffer data. That's way too slow. Instead, it hands over a capability token. Our microkernel just executes a WRPKRU hardware instruction to instantly flip the Intel PKU lock. Just like that, sexdisplay is granted read access to Silk Shell's memory. The memory itself is the transport. Let's hit section 4, invariants you cannot break. We have what we call a stop-first checklist. Before you even think about modifying these core systems, you have to stop and really justify it. Let me spell these out. You cannot introduce SD, lib, C, or standard threads into this environment. You cannot create direct cross-protection domain pointers unless they are properly, strictly capability mapped. Do not even attempt a shared frame buffer redesign. We've already solved that problem, let's not go backwards. You absolutely must preserve strict bounds checks on all frame buffer writes to prevent memory corruption. And finally, all interprocess communication must happen exclusively through our PDX IPC mechanism. We do not do silent hacks here. That brings us to our most critical visual contract, the Visual Liveness Guarantee. The contract states exactly this. Every compositor loop must produce either a UI frame or a distinct non-black idle frame. A completely black screen? That's an illegal system state for us. If the screen goes black, it means the compositor loop is starved, or worse, it's totally dead. Even if our IPC fails completely, sexdisplay is required to render a distinct visual state, like our signature cosmic purple base. That proves to us that the display driver is still alive and the kernel is cycling correctly. Finally, section 5, current development priorities. Our immediate execution roadmap is very strict, so let's get aligned. Priority 1 is keeping the master branch bootable and the system clock stable. That means no regressions that randomly freeze the compositor at 2 seconds. Once that's steady, priority 2 is locking down the renderer contract. We need to ensure that silkbar and sexdisplay perfectly respect the ABI. When that is rock solid, we tackle priority 3, wiring the pointer and keyboard paths all the way through sex input to Silk Shell. And rounding it out, priority 4 is going to be full USB HID support for a genuinely interactive experience. We're solving these linearly, one step at a time. So here's where we stand. The kernel is routing capabilities correctly, the physical Intel MPK locks are fully engaged, and they're holding our memory domains completely secure. The PDX pathways are wired up nicely between PKey 1 and PKey 3. We are literally one successful zero-copy PDX call away from rendering the Silk desktop permanently. Your move, architect. Are you ready to write some safe code and actually light up that purple desktop? Let's get to work.